This is part 2 of our oxidation reduction or redox reaction series. And in this presentation, we're going to focus on writing balanced half reactions. Our learning targets for today include being able to balance electrons in redox reactions and writing balanced redox half reactions. It is important to note that the examples we cover will be simple, and we will be using very general guidelines. In an upper level chemistry course or an AP chemistry course, oftentimes you will encounter redox reactions occurring in either acidic solutions or in basic solutions. Those types of problems require additional steps that we will not be covering in this presentation. Let's begin our exploration by examining this single replacement reaction between copper, metal, and silver nitrate in solution. Copper metal, shown here in this picture, is a malleable, ductile solid, and here it is shown appearing as a wire in a coil shape. It will be immersed in silver nitrate solution. Notice the state symbol for silver nitrate is aqueous. That means that silver nitrate is soluble in water, and here it appears as a clear, colorless solution. So this single replacement reaction will occur based on the activity series of metals because copper is more reactive than silver. So when copper is immersed in silver nitrate, this is what you will immediately see. Notice the copper metal coil, it looks like it's been coated with a white or silvery substance. Over time, you'll see that the reaction will cause the solution to turn this bluish green color, and the copper wire will continue to be coated with additional precipitate. So hopefully you can see that the coating is due to the silver ion precipitating out and forming a solid coating on this wire. Eventually, that copper wire can be shaken, and the silver, being in a very fragile state, can fall to the bottom. And if the person conducting this reaction wishes to isolate the silver precipitate from the solution, they can use filtration to separate the solid from the liquid. When they do that and let the liquid evaporate or put the sample into a drying oven, eventually you'll see silver here in its solid powdery form. Now that we've been able to see the changes that have occurred once the reaction finishes, let's look at what's happening with the electrons. So we'll start with copper. Copper, as you know, in its elemental state has an oxidation number of 0. Here on the product side, in an ionic compound, it takes on the oxidation state of +2. Hopefully you can see that there is a loss of electrons resulting in an increase in the oxidation number. That means that copper is the oxidized element, also known as the reducing agent. Next, let's look at silver. So the silver ion present here in this formula has an oxidation state of +1. On the product side, it is present in its elemental state, so its oxidation number here is 0. Notice that the oxidation number has decreased in value or has been reduced due to a gain of electrons. So for that reason, silver can be classified as the reduced element. Finally, we're going to take a look at the nitrate ion. Notice that the nitrate ion is present on both sides of the reaction. For that reason, we are not going to separate the two elements, nitrogen and oxygen, making up the formula. We can keep the formula intact. So the nitrate ion on the reactant side appears as a -1 ion, as it does on the product side. Notice that the oxidation number remains unchanged. That is why we can classify the nitrate ion as our spectator. Remember, spectators do not participate in the reaction. They merely are present. Let's begin writing half reactions for oxidation and reduction. We'll start with copper. Copper is the element that was oxidized. So its half reaction will show the electrons being lost on the product side. Notice copper in its neutral state on the reactant side by itself, producing the copper +2 ion. Next, we'll take a look at silver. Remember, silver gains an electron. So in the reduction half reaction, its electron will appear on the reactant side. Notice the difference in the number of electrons lost compared to the number of electrons gained. These numbers are not the same. When electrons lost do not equal the number of electrons gained, we consider that reaction to not be balanced. In order to balance the half reactions, we must balance the electrons. So the simplest way to make the electrons gained equal the electrons lost will be to multiply the entire equation, the entire reduction half reaction, by 2 to balance the electrons. So let's bring down some parentheses and multiply the entire equation by 2. When we distribute the 2 to everything in the parentheses, you'll notice that we have 2 silver ions, each with an oxidation state of +1, gaining an electron each. So that means 2 electrons to produce 2 silver atoms. Notice here the electrons that are lost in the oxidation reaction now are equivalent to the electrons gained. This means that our half reactions are now balanced. The next example we're going to cover is this synthesis reaction. But before we begin, because it is a slightly more complex problem, let's go over the general steps we will be following. So the first step will be to assign oxidation numbers to all of the atoms in the reaction, just like we did for the previous problem. Once we do that, we will write half reactions for the species being oxidized and the species being reduced. Afterward, we'll make sure to balance the elements in the half reactions. Once we do that, we'll check to make sure the appropriate number of electrons lost equals the number of electrons gained in the reaction. If that is not the case, we'll make sure to balance the electrons so that they cancel, or where the electrons lost equal the electrons gained. Let's start with step 1, assigning oxidation numbers to all the atoms in the reaction. So we'll start with iron. In its elemental state, iron is 0, and on the product side, in this ionic compound, it takes on the oxidation state of +3. Now let's look at oxygen. Oxygen here in its elemental state is also 0, and on the product side, it has the oxidation state of -2. For our next step, we're going to write the half reactions for oxidation and for reduction. So starting with oxidation, we can see that iron here has lost 3 electrons. So we're going to show that in our half reaction. Notice that the electrons lost appear on the product side, and you can see that the iron forms an iron +3 ion. we brought down a coefficient of 2 to show that there are actually 2 iron ions present here. Note that each iron ion is going to lose 3 electrons. So that should equal a total of 6 electrons. Let's go ahead and update the number of electrons lost. 2 times 3 should equal 6 electrons lost. Next, we're going to look at the reduction half reaction. So in this equation, oxygen is going to gain 2 electrons. Remember, oxygen is a diatomic molecule, so each atom will gain 1 electron. Okay, notice in the formula up above here, there are 3 oxygen ions. So we're going to bring in a coefficient of 3 to show that there are 3 oxide ions being produced in this reaction. Now, 3 times 2 is 6. So altogether, there are 6 electrons being gained. So we must go back and update our electrons. Okay, so now that we've updated our electrons on the oxidation and reduction half reaction, let's compare them. Notice that they are the same. This is ideal for balancing redox half reactions, but we are not quite done yet. Notice the elements on both sides of each equation. For iron, the elements are not balanced. For oxygen, the elements are not balanced. So we're going to move on now to step 3. Step 3 involves balancing the elements in the half reaction. So let's start with iron. To balance out iron on the reactant side, we need to bring in a coefficient of 2. Now let's look at oxygen. So on the reactant side, we have 2 oxygen atoms, and on the product side, we have 3. So remember, a common multiple, or the least common multiple of 2 and 3 happens to be 6. So on the reactant side, we'll start with bringing in a coefficient of 3. 3 times 2 gives us 6 oxygens. And on the product side, we'll simply replace the 3 with a 6. So 3 times 2 is going to give us 6. Okay, now that the oxygens are equivalent, let's make sure our electrons match the number that is supposed to be gained here. So 6 times 2 oxygens, that means we have 12 electrons that should be gained. So let's go ahead and update our electrons. Now that we've updated our electrons, we're going to look at the number of electrons lost and compare that to the number of electrons gained to see if they match. So on the oxidation half reaction, notice there's 6 electrons lost, and the reduction half reaction shows 12 electrons gained. So this again is not ideal. The 2 should match. Because they do not match, the reactions are not considered balanced. Let's move on to our final step. For our final step, we're going to balance electrons so that they cancel. And the easiest way to do that is to multiply the entire oxidation half reaction by 2 so that the electrons are equal. So let's bring in some parentheses and multiply the entire reaction by 2. When we do that, our balanced half reaction for oxidation ends up with 4 iron atoms producing 4 iron ions with a positive 3 charge and 12 electrons being lost. The reduction half reaction does not need to be changed. Notice the coefficients stay the same because the electrons were already at 12. Now that the number of electrons lost, 12 electrons, equals the number of electrons gained, also 12 electrons, we consider these half reactions balanced.